let's kick off today's lecture by visiting our old friend, the tree. And we're going to talk about traversing trees before ultimately going on to a new generalized version of a tree known as a graph. So I'll start by just reminding you what a tree is. So a tree is a set of nodes, and it's a set of edges that connect those nodes with the constraint that there can only be one path between any two nodes. So the three objects on the left are trees, they're in green, and the two objects on the right in pink are not, because they have multiple paths between two nodes. Now, second definition to remind you is a rooted tree. A rooted tree is a tree where you've chosen one node and said, hey, you're the root. And at that point, that gives us the idea of parent and child. And the idea is that a parent of a node is the first node on the path from that node to the root. And then a node with no child, reminder, is called a leaf. So all trees can be made into rooted trees immediately by just saying, you are the root. So I bring this up because we're going to go beyond trees. And it's important to realize as we're doing this that while in this class so far, we've used trees as mostly a data structures concept. That is, it's a way to arrange nodes to implement a search tree or a trie or a heap or disjoint sets or something else. We've seen trees used in this manner, okay? And in these many different ways. Now, trees actually are a more generic concept. It's not just a way to arrange nodes in a data structure, but it's an idea. So for example, an organization chart for an organization is a tree. You have a president, you maybe have some vice presidents, you have some managers, and so forth. Family lineages, right? So, oh no. Anubis got short shrift. Not good. Don't mess with Anubis. So here we look and we see Atum-Ra as the patriarch of the whole entire Egyptian god's family tree according to this random image from Pinterest. And then you go down the line and you eventually get to Anubis. So this is a tree also, right? It could be used as a way to track trees. And then here is just some random training manual for the management of malaria that I found. It is also a tree. It's a sequence of decisions that you make in trying to manage malaria. So if someone has a history of fever and they are under 5 and they show signs of severe malaria, you should treat as severe malaria, of course. But this is where it gets more complicated as below. Okay, so trees. They could be used in many contexts. It's not just a data structures thing. It's a life thing. Okay? So sometimes knowing that trees are general purpose objects, sometimes you want to iterate over a tree. Maybe I want to print out the names of everyone who works at the company. Who knows what? Or let's suppose you want to find the total size of all files in a folder called 61B. Well, it turns out that file folders on a computer are also a type of tree. Here, I have a folder named 61B with 2 folders named Proj 0 and Homework 1 and perhaps some others. And let's say I want to print out the total size of all the files. Well, in that case, we need to iterate over this tree. And what you might usually call tree iteration is actually called by people in practice tree traversal. Okay, so it's not tree iteration. Nobody says that for whatever reason. They say tree traversal. Now, unlike a list, where there are many different ways in which unlike a list where you can basically go either forward to backwards or backwards to forwards, there's actually many different natural ways to visit nodes in a tree. And each of those orderings we'll see is different is useful in a different way. Okay? So let me give you an example of a natural ordering for a tree. One of them is so-called level order. In this approach, you visit your nodes in a top to bottom, left to right order, like reading in English. So first, I will visit D, because it's at the top level. Then I'll visit B, then F, then A, then C, then E, then G. So that's one very natural way that we could visit a tree. Now there's 3 other very natural orderings that are called pre-order, in-order, and post-order. And all 3 of these are known as depth-first traversals. And the basic idea, though it'll make more sense once we see some examples, is that we're going to traverse deep nodes like A before shallow ones like F. Now I'll note that traversing a node is different than visiting a node, and on the next slide I'll show you what I mean by that. So here is the pre-order traversal of a tree. So in this approach, what happens is that if the node we're looking at is currently null, we're just done. In this case, for this pre-order implementation, we're going to print out a node a node's key first, and then we'll do the pre-order traversal of the left, then the right. Okay, this is how we define and preorder. It's a recursive procedure. Okay, so the basic idea is you visit a node, and then you traverse its children, left and right. Okay, so for example, if I start at the root, I will visit D, I'll print it out, and then I'll preorder traverse the left tree. So what's the root of this side? Well, that's B. So in that case, we print it, and then we traverse the left side. So when we get here, we visit this node, then you traverse its left and its right. Those are both null. So then you go back up. You finished B, and so now you need to preorder traverse the right side. So you'll do C, then go back up, then you go back up to D. You have now finished preorder traversing D's left side. So now I'm going to go to the right. So when I call preorder on F, I print out F, and then I preorder traverse E, which means printing it out and doing its children. Come back up, do the right, that's G. Okay, so that's the preorder traversal. By contrast, the in-order traversal looks like so. So in this case, what I will do is I will first in-order traverse the left side, and only then will I visit the nodes. Okay, so in this case, with an in-order, we traverse the left child, visit, then traverse the right child. So when we start at D, we don't print yet. We're not going to visit yet. We're actually going to finish the in-order traversal of the left side. Okay, we're not going to print yet. We're going to finish the left order traversal, or the left side. So when I do an in-order traversal here, left side's null, then we print out A, then we print right, and then we go back up to B. Now since we've finished the left side, we can now print out B, and we need to go in-order traverse C. Well, there's nothing to do down there. It's just one node, so we're done. So now we've finished the entire left tree of D, right? We've completed in order of D, so now we print out D. Next, we go to F, but we don't print it yet. We need to finish its left tree first. So we traverse the left tree, visiting all of its nodes, that's E, then we go back to F, then we go to G. Okay, great. So that's an in-order traversal. And so next, and finally, let's discuss the post-order traversal. In this case, you'll traverse the left, traverse the right, and then visit. So I'd like you to try and figure out what the answer is here. Pause the video, and it's going to be one of these 5 answers. Okay? So the correct answer is A, C, B, E, G, F, D. Now, just to give you a brief understanding of why, I don't want to step through this in as much detail, because hopefully you just did. What happens is, before we can print out D, we need to finish both of its left and right-hand sides. And that's why D ends up on the end. And so I'll leave it to you to carefully walk through this to convince yourself of this answer. Now, one handy trick, right? So you might have found it a little tedious to step through all this code. So I will teach you a nice, useful visual trick that humans can use, not algorithms, which works like this. So the preorder traversal, one way to do it is we trace a path like around the graph. Imagine just taking a piece of paper and drawing a line around the graph. And then we're going to go counterclockwise. And then we're going to visit for a preorder traversal every time we pass the left side. Okay? So it'll be like 1, 2, 4, 5, 7, 8, 3, 6, 9. That's the preorder. The in order is every time you go under. So it'll be 4, 2, 7, 5, 8, 1, 3, 6, 9. Okay? Or the post order will be the same thing, but you'll visit when you cross the right side of a node, or the right of a node. Okay, so I go around and I get to 4 and I say 4, okay, 7, 8, 5, 2, 9, 6, 3, 1. Okay, so that's the post-order traversal. So it's a useful trick that I find very handy when I'm just trying to work out these problems on paper. But again, an algorithm, it's not going to have access to a drawing of the graph, so it's just going to have to do the easier recursive code. So the last question you might ask yourself is, why do we care about all these traversals? What good are they? Like, why do I need a pre-order and a post-order and an in-order? In a list, I mean, if I iterate forwards versus backwards, it's basically just the same thing. Well, in a tree, I'll give you an example why pre-order is neat. So pre-order traversal would be, for example, a useful choice for printing out a directory listing. So this right here is a tool that I wrote many years ago when playing StarCraft 2. In that game, the matchmaking system was a 1 versus 1 game, And the matchmaking system would occasionally match you with people who are either way better or way worse than you. And the game involves a lot of clicking, and so I didn't want to waste effort on people that were not very good. So I wrote a tool that would, because of various issues with the way the game is built, I could tell how fast the other person was playing. And that's why it's called SC2 APM. It's trying to assess the actions per minute of the other player. So if the other player was playing slow, I knew I could relax. And it was very handy. So anyway, this is the directory structure from this actual real tool that I built and used for a while. And let's say I wanted to print out the files in this folder. So that backstory is not important, but thought you might find it interesting. Anyway, so if we do a pre-ordered traversal, we'll start at the root, and we'll just print out the directory name. And then, since it's a pre-ordered traversal, we're going to go left, and then every time we go down a level, my recursive method will add a couple of spaces to the front. So now I print out direct overlay, I go left, I print out direct IO, I go left, I print out d3dd11m.cs. I finish this side. Okay, so now I continue my pre-ordered traversal, I print out injector, and now I return, and so I'm back up one level in the tree. So the pre-ordered traversal hits directo.suo, and you'll see it's printed at the next level down. And so hopefully you get a sense. I mean, I haven't gone through it in great detail, but pre-ordered traversal is the natural choice for doing a directory listing. And if you think about trying to do this with the in-order or post-order traversal, you'll see you don't get this nice diagram. Another example, let's say post-order. What good is that? Well, it's useful for gathering file sizes. So let's say I want to go through and print out the total size of all my subdirectories. I want to do basically the same thing, but I want to capture the size of each folder. So in this case, my code might look something like this. If x is null, if we're not on the tree anymore, that's of size 0. Then we'll have a total, and how it works is we will add the post-order size as calculated as all of my children, and after I've done that, I will add my own file size and then return total. So for example, when we do the post-order traversal, we'll start at the root, we go to direct overlay, we go to direct IO, we go to d3d11.cs. It returns this number, it goes up here. However, we don't visit direct IO yet. We haven't finished all of our children, so we're still iterating over this loop. So we're also going to add 8,798. Now having added these two numbers, we have 27,179. We're done. So we go back up. So then direct overlay, its left child has now finished its job. So the post order call to direct IO is done, and we're going to add this number to the total that direct overlay is tracking. We will then add the second child and the third child, and we get 66,972. We then come back up to SC2 APM. It has finished its left child, so now we're going to add the middle child, and then we need to add the right. Well, we have to wait until that is done before we can capture that information. That is, we're making a post-order call to Python, so it's only once this tree is done and this value is available that we're now finally able to compute the value at the top of the tree, which is 68,170. Okay. So that is an idea of why traversals are useful. So now at this point, you know what the traversals are and roughly why they're useful. And so what we're going to see in the next video is how we can generalize things yet further.